Hello everyone, my name is Muhammad Al-Hadi and today I'll present our work titled Analytical and Numerical Analysis of Electrostatic MEMS Resonator for Sensing and Filtering. Here is a brief overview of the presentation. I'll begin with a quick introduction to MEMS and resonators, followed by relevant literature, problem formulation, model development, results, numerical validation, and conclude with future directions. MEMS stands for Microelectromechanical Systems. These are miniaturized mechanical and electromechanical devices often fabricated using microfabrication techniques. They offer benefits such as reduced volume, low power consumption, and cost-effective mass production. MEMS are widely used in fields such as biomedical devices, automotive systems, and consumer electronics. MEMS types include sensors, actuators, radio frequency MEMS, micro-optoelectromechanical systems, and bioMEMS. Examples range from capacitive pressure sensors and electrostatic actuators to radio frequency switches and drug delivery systems. Each type integrates mechanical and electrical components at the microscale. MEMS resonators typically consist of a vibrating microstructure actuated near its natural frequency. They are used in sensing, frequency filtering, and signal processing. The vibrating microstructure can take various shapes and forms, such as beams, plates, diaphragms, or a combination. However, we will be focusing on the beam plate configuration in this presentation. The earliest work on such a configuration was done by Dr. Naifi et al., in which they developed a distributed parameter model for an electrostatically actuated capacitive resonator used for gas sensing. On the other hand, the latest study was conducted by Dr. Ghumaim et al., in which they explored the potential capability of an electrostatic MEMS resonator composed of two microbeams attached to a microplate coated with metal organic framework to detect CO2. Now, due to the promising experimental results of the sensor used by Dr. Ghumaim, we decided to produce an analytical model to further explore its static and dynamic behavior, which is difficult to predict due to 1. The complex interactions between mechanical deformation and electrostatic forces, and 2. The nonlinear coupling in beam plate configurations. We opted for a distributed parameter model over a lump parameter model because it offers more accurate and physically representative predictions. The geometry of the resonator is comprised of a rigid microplate connected to two identical symmetrical cantilever beams, as shown by the figure on the right. We assume that the beams follow Euler-Bernoulli theory and that the microplate is rigid. Electrostatic actuation is applied via a fixed electrode located beneath the plate. We then formulated expressions for the total kinetic energy and the total potential energy as shown on the slide. The kinetic energy includes translational and rotational components, while the potential energy consists of elastic and electrostatic contributions. These expressions were then plugged into Hamilton's principle to derive the governing equations of motion and boundary conditions. Non-dimensional variables were then introduced to simplify analysis. The table below summarizes the geometric and physical parameters used in our model. You can refer back to the previous figure to see how each parameter corresponds to the resonator's dimensions. For the static analysis, we set all time-dependent variables to 0 and solved the equations using Mathematica. We found a pull-in voltage of approximately 16.4 volts, at which point the beams deflect by 25.21% of the total gap distance. For clarity, the pull-in voltage represents the point where the beams collapse and stick to the electrode due to the excessive electrostatic attraction, potentially leading to sensor failure. We also solved the eigenvalue problem to extract natural frequencies and mode shapes of the sensor. The first four bending modes are shown here, with corresponding natural frequencies of approximately 52, 568, 899, and 1769 kHz, respectively. Then, in order to solve the pre-stressed eigenvalue problem, we linearized the electrostatic terms and introduced them into the governing equations. The result shown on the right shows that the first natural frequency decreases with increasing voltage, confirming the softening behavior due to electrostatic loading. To validate our model, we built a finite element model in COMSOL, shown on the right. The material used is polysilicon with a Young's modulus of 160 gigapascal and density of 2300 kg per meter cubed. The numerical static response matched closely with our analytical prediction, as can be seen by this figure. These figures here display the first four bending mode shapes as obtained from COMSOL, which match the analytical mode shapes I presented earlier. As for the natural frequencies, the table shows a comparison between the analytically obtained and numerically obtained natural frequencies. The first two natural frequencies have a close match. However, the third and fourth natural frequencies deviate slightly, likely due to the rigid plate assumption. In reality, the plate is flexible, which influences the higher natural frequencies. On the other hand, the voltage-dependent softening trend observed numerically has a close match with the analytical prediction, as shown by the figure on the right. To summarize, we developed a distributed parameter model for an electrostatically actuated MEMS resonator composed of a rigid plate and two cantilever microbeams. Using Hamilton's principle, we derived the full governing equations and boundary conditions. We solved for both static and dynamic responses in Mathematica and validated our model using FEM simulations in COMSOL, observing a strong agreement. Future work will focus on applying the Galerkin method to reduce the governing equations to a nonlinear reduced order model. This will allow us to investigate rich nonlinear dynamics such as nonlinear resonance and bifurcations, with applications in ultra-sensitive mass sensing and precise frequency filtering. Here are my references. Thank you for your attention.